Hello friends, so welcome back. So today I will continue on this idea of GMM HMM as it is applied to speech processing. Okay, so I have purposely retained the place where I stopped last time, and just to remind you, right, what is the problem that we were talking about last class, right. So the whole problem is we are trying to now find out, in my language there are only two words that I say, yes and no. Okay. So given that yes and no, what do? I have to, again it is a binary classification problem, there are only two words. So any so what do? I collect a lot of data. So I collect some 1000 utterances saying yes from different people, and similarly some another 1000 utterances saying no from multiple people, right. So yes and no, right. So there must be some more data here. So similarly for no also I will use a lot of data. So let me just see if I did that. Yeah. So I will be collecting a lot of speakers data with no also. Okay. So so this will be some 1000 speakers again who are saying no. Okay. And the problem we pointed out last class is that I do not know in practice where there are three sounds involved in yes and no, right. So in yes, let me take the yes, the same idea will hold true for no, is that when I say yes, there are three distinct sounds that I produce, phonemes, right. Yeah, s, yeah, s, right. So therefore the feature vectors, remember we are always for classification, we are looking for feature vectors. In our case, we will always take the log filter bank features or MFCC features, right. So but the problem in this case is that I do not know which of these features belong to the sound ear, which of them belong to a, and which of them belong to s, right. So I could uniformly segment, right. I can divide the entire interval. Let us say I take the first utterance which I know belongs to the sound word yes, divided equally, this 100 guys divided equally, and so 33, 33, 33, or one of them will be 34, you will divide it equally and you will get, right, another utterance, because all of us do not speak at the same rate. Another person took 94 such feature vectors, same yes sound, then again 94 I divided 31, 31, 31, 32 or something like that, and again I partitioned it. So like this I partition for all the 1000 guys, and so I collect all the year and from this and build a, so this is like the random initialization we did in the Gaussian mixture, where we did not know the category information. Did that belong to category 1 or children, or did it belong to parents or something? That information was missing, right? And we built a random model, and then we assigned labels to it, pseudo labels. Again we reiterated and so on and so on. Same idea we are coming to this place also, that given this random uniform segment, not random but uniform segmentation, we now have some vectors which we say belong to ear, may not be right, some which belong to a and some which belong to s, right. Then with this I can build a mixture of Gaussians. I need a mixture of Gaussians because different people say different ear in different ways, children, adults, males, females. Males itself, there are so much variations, right. Environment, noise, accent, so many things will influence these things, right. So we need a mixture of Gaussians. Similarly a and s. Now I have a model for each of these sounds, right. So given the model for each of these vectors, I can go back and assign to which model does it belong, right. And now that is where the hidden Markov model will come and intelligently do it. So suppose we are able to do, because we have now got a model, right, it is no longer uniform segmentation. Some of them will be strongly towards ear, the middle part of the vectors, the middle part of these vectors will be towards the sound a, and the last part will be towards the sound s, right. So the segmentation now can be at a different place. Only up to 17 vectors belong to ear. A is from 18 to 78 for the first guy, right. This was different from the uniform, where I took, there were 100, I uniformly divided into 33, 33, 33. But after building the initial model, now it reduced, if the first part is only till 17, from 18 to 78 is A, and from 79 to 100 is Sir, right. Similarly, when I look at the second guy here, it was 94, which I divided equally into 31, 31, 32 kind of thing, almost equal. But here it might be very different. Here it is, instead of 31, it is 23, and from 24 to 84, and instead of the last one being again some 32, it is only about 9 of them or something, 10 of them here, right. So, that again became different, right, because now we have some model that captures it, right. And the last, like let us say the S1000th vector, the 1000th utterance, there were 76. So, here we said we will divide by 3, again it is about 25 for each one of them, that is why we put 0 to 1 to 25, 26 to 50. But again the last guy here might be very different, only 19 was and 20 to 58 was and then 59 to 76. Now, again my labels, the vectors that are associated for y have changed. Since the vectors of y have changed, my Gaussian mixture model will get different, right. So, I will update, I will get a new better estimate of the y. Similarly, I will get a better estimate of the A model, and similarly I will get a better estimate of the SIR model. Again I will repeat by segmenting it, again I will compare with all the 3 GMMs for each one of these S1 vectors, then the S2 and so on. Again what will happen? My segmentation will change, right. I will now get a different vectors assigned to different guys and so on, and so we keep repeating it, okay. But still this is not going to solve the problem that if I gave you an so now I have a GMM for IY, I got a GMM for EH, and I got a GMM for SIR. Similarly, for the no also I could get a GMM for N and the GMM for OW, right. So, these are all I got, okay. But this is still not good enough for, I mean I can do something, but it is not very efficient or it is not an easy way. So, given test utterance, so this is some test utterance I am going to get. So, some y1 of t, right. So, some y1 of t I will get, right. What is my problem? To decide whether yes or no, what was said, that is the problem, whether yes was said or no was said. So, remember in my language there are only yes and no, okay. So, now from this test utterance, so this is y test, right. So, I will get some O test 1 like this, by partitioning it, I will get so many things, O test 2, some O let us say 80, O test 80, right. Some intelligent clever person might say, hey, yes is going to be longer than no, I will use that to distinguish between yes and no. Isn't that a good idea? We are talking about very general, okay. In this specific case, yes and no, right, we think yes is going to be longer than no. So, I could use that, but look at a general case, maybe I am saying words of equal length, I am going to now deal with real speech, right, every kind of I can say hundreds of things, and somebody said yes, or somebody said no, right, or a lazy person. So, I have to worry about lots of things, right. So, we will take the more generic approach that should work irrespective of whatever the ideas are, okay. So, irrespective of whether I am only talking about a long and a short word or something, okay. So, now the question is this, given this, how do I decide whether it is yes or no, right. So, I need some good way of doing it, right. And again I can't say that look at the GMMs for IY, and you could do that, and then for the GMM of year add up those probabilities or something and do it, okay. But this is actually where the idea of sequence modeling is going to come into picture, and if you use HMMs, it is going to become very, very easy, okay. So, now I am going to recall what we did in HMMs, okay. Recall. So, what were there? So, there was the hidden Markov model, okay. In the hidden Markov model, what was the hidden state? The hidden state was weather condition. Which was sunny or cloudy or rainy, right. So, these were the 3 conditions. For these we have the transition probability. Transition probability, which says, so given sunny or cloudy or rainy, what is the probability that the next time it will be sunny or rainy or cloudy, right. So, that is what is going to happen, right. So, these are the probability of S given S, right, or probability of C given S and probability of rain given S, something like that. So, that is what we have found from historical data, right. Then we had the observable state. Observable state. Okay. What is the observable state? The observable state had this kind of, let us say 4 things: dry, dryish, damp and soggy, and this had certain probabilities, right. So, there was a probability of this being 0.6, then this being 0.5, 0.3, 0.1, something, right. And similarly, this guy had again certain probability of generating dry, dryish, damp and soggy, right. And similarly, this guy had also a probability of dry, dryish, damp and soggy. And what was the basic problem? So, we were asked, given I observe some given let us say 5 consecutive days or 3 consecutive days, dry, dryish, dry. Okay. Which underlying weather condition, most sequence of weather condition best explains this observation? Or states, right. So, we will keep, this is what we call best explains this observation. Dry, dryish, dry, right. And so, what did we do? We said this, how can we solve this problem given I observe this dry, dryish with underlying sequence, which one? So, we said let us consider underlying sequence to be let us say sunny, cloudy. Okay. This is one of the possible weather sequences, right. How many weather sequences can be there? So, 3 raised to the power of 3, 9 possible weather sequences are there. This is one of them. So, for this sequence to generate observations dry, dryish, dry is how, what did we say? We said this is going to be done by a combination of the transition and the observation probability. So, what did we say? This is probability of dry given it is sunny, and we have to start some initial state. So, initial state was cloudy or something, initial is cloudy. Okay. So, that previous day let us know that for sure we know cloudy given by probability of sunny given cloudy. So, this accounted for the first part of it. So, the first part of this is accounted here, then probability of the second guy, right. So, multiplied by probability of dryish given sunny into sunny to sunny had to happen. So, probability of sunny to sunny, this was the second part of it, right. This was the second part which was captured here, right, sorry. This was the second part which got captured here, and the third part of course is probability of sun dry, given that probably the weather condition is cloudy, and this transition probability of cloudy given sunny, right. And this third part is what is represented here, correct. So, now you have a combination of both. So, these guys are all observation probability and these guys are all transition. So, the other guys are all transition these are the transition probabilities, right. So, for weather condition we knew that we needed two things, the transition probability and the observation probabilities, right. So, the observation probabilities, both of them we needed, right. So, this guy tells, given that I have historically given sunny, how often did sunny happen, given sunny, how often did cloudy happen, given sunny, how often did rainy happen. This guy is telling that if I am in the sunny state, outside sunny, I am in a very deep cave, I cannot say outside rather, but the person comes and tells me that the grass is, I mean outside is sunny, and I find that whenever he does that, the grass is dry most of the time, 50% of the time. That is how I am getting that 50% that I am talking about here, right. So, that I have observed for so many years and I have come up with this conclusion, right. So, remember that we are talking about these observation probabilities, transition, observation, transition, and observation transition is how often sunny follows sunny historically, and observation is given that I know outside weather is sunny, how often was the grass which I can observe. The only thing I can observe is the grass, right. That is why it is observable. What is hidden is I do not know what is the outside actual weather, right. But historically somebody told me whenever outside was sunny, I noticed that 0.5 or 50% of the time it is dryish, 30% of the time dry, and 30% of the time it is dryish. That is something that I figured out, okay. And then we can start finding out that given the observable state, given that dry, dryish and dry, I look at all these combinations, 3 raised to the power of 3, 9 combinations, and find the maximum, and this we can do efficiently by the idea of Viterbi, right. So, we are going to use efficiently by Viterbi. Now, this is just a recollection of what we did before.